a kind of a weird setting here. Okay, so I think I can put this down or something. Let me see. No. Well, so let's get started. Welcome back to the software testing and the quality assurance class. And I do have your graded midterm exam, and actually I had them ready last week, but we did have some unresolved issues, and now they are resolved, and so I can return the graded homework, the midterm exam back to you. And so before I do that, let me give you the summary first, okay? And let me grab one of this. Mouse here. Desk camera. Oh, where is it? Oh, okay, it's here. It's kind of weird. Let me try to move it. Can I? Nope, that's tilt. See how? That's kind of really hard for me to reach there. Web conference, room control, shutdown, and zoom focus. I don't know if I can move this camera this way a little bit, but at least I can zoom in a little bit. Yeah, okay. Yeah, that zoom helps, but well. Okay, I kind of want to move it this way because it's kind of hard for me to write anything. Camera, this one. Oh, good. This one works good. Yeah, that's better. But I don't know if I can. No, that's a tilt on the pen, and only front back. Okay, so I'll try to live with that. Okay, so this is the midterm exam. Okay, and so if you are thinking of what we were doing with the testing, okay, and you know that this is a typical boundary testing problem, right? The exam. So what we have here, we have upper bound and we have a lower bound, right? The lower bound is 0. Nobody can get a negative score, and the upper bound is 100. So this is the theoretical max and the minimal. Okay, and then we do have the distribution here. For the actual class, so this is the absolute scale here, but we do have. I'm happy to report we don't have anyone near 0, so that's good. Okay, and so the lowest is actually 66. Okay, so that's our minimal is 66. Okay, our max is 98. Okay, so I'm pretty happy about this, and particularly with the distribution, because I don't think we have too many people in the 60s, and in fact, we only had one that's kind of like an outlier in the 60s. Okay, so just one in the 60s, and then we have the rest spread out somewhere around there, and we had some people in the 70s, and I think more people in the 80s than in the 70s. Much more people in the 80s, and several in the 90s. Okay, so that's the kind of distribution here. So mostly in the 80s. Okay, so most of the people are in the 80s. Okay, and several people asked me about what's the interpretation of this numerical score in terms of the letter grade A, B, C, D we use here. As I can tell you, on kind of the average for SMU classes at this level, they're beginning graduate level and some senior undergraduate electives, their average is around B plus. Okay, And so if you are somewhere around the average, you should be assured a B plus. Okay, so that's the general interpretation. And so if you are in the 90s, you are definitely in the A range. Okay, high 80s probably kind of like the A minus. The mid 80s is a kind of like a B plus. Low 80s and 70s, high 70s is probably in the B range. Low 70s and it's probably B minus, and 60 is probably in the C range. So nobody had a terrible score. Okay, and everyone have a kind of a passing grade here. Okay, so that's the distribution here. And let me return the graded midterm exam to you, and then I'm going to go over the exam questions. Okay, one of the reasons to do this is that if you did have some kind of doubts about a certain points and things, we can kind of go over some of the things, so clarify some of the things that you may have questions, may have doubts, and even if you did almost perfectly in the high 90s, it can still you can probably still benefit from hearing a few other different ways of doing similar kind of things. Okay, so that's what we are going to do in the kind of first segment of today's class. And then after that, we'll take a break, and I will try to finish up the chapter 10, the rest part of chapter 10, basically the usage-based statistical testing based on enhanced finite state machines. So we enhance the finite state machines into the so-called Markov chains, and so we will be doing that as a part of the rest part of today's class. So let me return your graded homework, the exam, midterm exam. And actually for the distance student, actually you were a little slightly ahead of the on-campus student in this respect, because I think yesterday I gave all the graded exams for the distance student to Deborah, and she actually sent back a scanned copy of the graded exam. So you should have received your graded midterm exam by now. It should be yesterday. Okay. So let me distribute the graded exams to the in-class student, and then we can go on from there. Okay. Matrix, Bavici. Not here. Abdullah, Hababri. Yasmin, Fazunzi. She's not here. Zhenhe Li. Ali, Ahmed. So, Oli. That's me. Prima. Shwana, Daruli, Al-Habi. Anshumali Mishra. One Sumi. Chelsea Rico. Zhe Yang. Jeffrey Atticus. down. Lawrence Cleveland. Ian Tolley. Laura Toledo. Albert Hayes. So you are officially distant, right? But right?
Yeah.
Okay. 有区别的引发的所谓尼库Ferreira. Vinay Louisiana. Not here. Vidrak. So Yasmin is not here, Renee is not here. Okay. So wait, just making two results. Let me see if I have a clean copy of the exam somewhere. Okay. Oh yeah, I do have a clean copy of the exam. Okay, what I'm going to do next is to go over the midterm exam questions with you, and so we can kind of talk a little bit about what is the correct answer, and sometimes what is a correct answer, and what are the other ways to answer some of the questions that make sense as well. Okay. Okay, so the first set of the questions are the multiple choice questions. Okay, so multiple choice questions. So we have the remember some of those multiple choice, some of those questions you may have several of the logically correct answers, and you are supposed to find the best answer for that question. Okay, so the thing is that typically people, some people make some mistakes here and there, but I'm happy to say there are quite a number of people answer all the multiple choice questions correctly. So that's good sign. And okay, so the first one of the multiple choice said from a customer's perspective, quality is associated with. So we are talking about quality from a customer's perspective. So we talk about the different views, and so this is a kind of like the customer view. And so the first one said the correct external functionality. Okay, this is definitely something from the customer's point of view, and they see quality as that you have a correct internal functionality. So definitely it should be a good candidate. Okay. Let's look at the others, whether we have some better choices or maybe all of the above. Okay, but A is a good candidate. The second one said the correct internal implementation. Correct internal implementation is very kind of far removed from the customer perspective on quality. They typically don't care about your internal things as long as the external things works for them. That's fine. Okay, so that is actually the whole basis for us to do this so-called object-oriented design methodology, and doing all kinds of other things. Okay. So B is not a good answer, but A is still a good candidate. C said low cost for the software product. that is something for the customer, but it's more to do with the cost than to do with the quality. Okay, and so we are talking about the quality. We are not talking about the other things. Typically, in software engineering, we separate the cost out as something that as a separate thing, as a compare and contrast to quality. You say cost, quality, schedule, and something like that. So cost is typically not considered as a part of the quality. Okay. D said low development cost. Development cost has almost nothing to do with the customers. They don't care about the development cost. Okay, if you have a low development cost, then that means you are efficient and you can make some more money. And but if you charge the same amount and as equally as good, customers will still pay for that, and so that you will be happy and the customer will be happy. Okay, so it's a kind of somewhat irrelevant to customers. So A. So far is the only one that is the best choice. Okay, so I know a number of people selected C. Okay, said low cost for the software product. Okay, the reason I consider A better than C is that the cost is typically considered as a separate attribute about the product. Okay, so cost is typically separate from quality. I'm talking about the quality. Okay, here. Number 2 says this is not important quality attribute, so it is a not one. Okay, so some people maybe say, oh, okay, this seems to be reliability is the important one, so I should pick reliability. I think a couple of people picked the reliability because they thought that they think that's the most important quality attribute. Okay. So we are talking about something that's not an important quality attribute. Okay, reliability is a quality attribute. So because our question says that this is not one, and so you cannot pick that one. Okay, it is one. Okay, B, safety. We talked about reliability, safety. Safety is also an important quality attribute. Okay. Usability, we mentioned about it a number of times. It's an important quality attribute. Okay. Cost, it's not. Okay, and so this actually the first two questions are kind of somewhat related. Okay, a little bit. Okay, so if you mess up on the first one, you might mess up on the second one a little bit. Okay, cost is not, and maintainability is, and portability. So if you remember, we talked about the so-called LTs, the external quality attributes. Actually, here. Besides the cost, all the other things are the so-called LT attributes of the external quality attributes for software products. Okay. So the correct answer is D. Cost is not an important quality attribute. Okay. Number 3, testing is more closely related to the following aspect of defect. Okay. So testing is doing what? So we are basically talking about errors, faults, and failures. Okay, testing is related to which aspect? Okay, A said defect prevention. Testing is not really about defect prevention. It's about defect already being there. Okay, if you are looking at the defect prevention, you are not really looking at the testing. Okay, error blocking. Error blocking is actually one type of defect prevention. Okay, you block the errors. Okay. Error source removal, that's another type of defect prevention. Okay, and then the next one, D said failure observation and fault removal. That is the closest. We are observing failures through execution and remove the faults that lead to those failures. Okay, so it's a failure observation and fault removal. Okay, and sometimes we just say is the defect reduction or defect removal. Okay, and the last one said fault tolerance. Testing is not really fault tolerance. Okay, fault tolerance is that you allow fault to be in the system but not causing failures or causing severe problems. Okay, so the actually this D is really kind of what we do with testing, observe failures and removing faults. Okay. Next one, number 4. the main advantage of inspection over testing is, so that's talking about the comparison between inspection and the testing. So they both have some of their own individual strengths and individual weaknesses. So now what I'm asking you is only about the advantage, the main advantage of inspection over testing. Okay. The number one, the A said inspection is more widely applicable. Yes, that's true, because you can inspect anything. For testing, you have to have some executable code to test. So the inspection is definitely more widely applicable than testing. So it's one of the major advantages. Let's see if there are some better answers than that. The second one, B, said inspection is more effective in finding dynamic timing problems. That's completely wrong, actually. Inspection is typically not as good as testing with dynamic problems. It's with static problems, logical problems, inspection is generally better, okay, because you are applying human intelligence and logic to inspection, okay. While testing, you are doing the dynamic execution. So dynamic execution and timing-related problems are more likely to be reviewed in testing than in inspection. So B is actually completely wrong, okay. And C said inspection relies more on human inspectors. That's true. Inspection relies more on human inspectors. But is that an advantage over testing? We cannot really argue that's an advantage, okay. You rely on human inspectors, and we know that the professionals are getting paid not peanuts, okay? And so they're expensive, okay? So if you have a lot of human inspectors to do the inspection, it's going to be costly. So although the statement itself is true, it's actually something that can be said about this is actually one of the limitations or disadvantages of inspection, because you cannot really automate much of the things, so you have to use a human to do it, so it's going to be costly. Okay, so the statement itself is true, but it's not an advantage for inspection over testing. Okay, so see here, you can see here, the statement is true, but the statement is not answering the question. I'm asking you about the main advantage of inspection over testing. Okay, so the next one says inspection is less time consuming than testing, which is debatable. So we don't know whether it's always true or always false. Okay, so depends on how much inspection you are doing, how much testing you are doing, and the different scope and the depth you are doing. So it's kind of questionable. It's not one of the best answers, and also it's not really we cannot say this is a major advantage because we don't know for sure whether inspection is less time consuming. Last one said the inspection has a well-defined procedure, such as in Fagan inspection. The statement itself is true about the Fagan inspection things. So when you look at the formal inspections, typically you do have a formal procedure, such as in Fagan inspection. But that procedure is not one of the major advantages, because the testing you can have a very formalized procedure as well. Okay, and also the advantage is not really procedure-wise. It's really in terms of the applicability and the effectiveness for some type of problems. So our applicability is the first one that says inspection is more widely applicable, is really directly addressing the question asked here, the comparison between inspection and testing, and that is one of the main and major advantage of the inspection. Actually, most people would argue that is the most important advantage of inspection over testing, okay? Because you can do it anywhere, okay? And the next one, number 5, formal methods include, okay, A is a formal specification, B is a formal verification, C is a formal systematic testing. Okay, so here we are talking about the formal methods in our specific meaning in our QA. Okay, in our QA, when we talk about the formal methods, we are talking about formal inspection, formal specification, and formal verification. So it should be A and B above. Okay, so that's basically the definition we have about the formal methods in the QA context. Okay, a number of people consider formal systematic testing as a formal method, but they are not really considered as a formal method in the quality assurance community. So it's just a basic definition here. You say, oh, you don't agree with that, then too bad. That's what we use in our class. Okay. The next one, number 6. Okay. Consider quality planning in SQE and the test planning in testing. Okay. A said they are the same. Well, they are not exactly the same, so I don't want to say they are the same. B said they are different. Yeah, they are different, but kind of whenever you pick two things, as long as they are not identical, they are different. So it's not really telling too much. Okay. C said they involve similar elements such as setting goals, selecting strategies, and planning for measurement monitoring. That is actually kind of captures what do you do in planning. In test planning, you test the goals for testing. In QA planning, in the SQE process, you set the overall goals for your QA and SQE activities. And then you select, in testing, you select your testing strategies, techniques. And in QA, you select, I'm going to do testing, inspection, and something else. For example, that's your QA strategy. Okay. And then you are also going to monitor the activities of those things that you are doing. So C is definitely better than A or than B. Okay. And D said all of the above, that's not quite true, and none of the above, that's not true. So C is the best one. The only thing that sometimes people say, oh, they are different, that's kind of too vague. Okay. When you have an answer that's that vague, it's probably not going to be a good answer. Okay. So basically, the thing, as long as any of the two things that's not identical, you can say they are different. But C is much more informative about the what they are doing in quality planning and in test planning. The last one is actually 4 mini questions. Okay. So in a sense that this one should worth a little bit more points, but I kind of try to keep things simple so that it's still 4 points each. And so here you have 4 answers for 4 points, and all the others you have 1 answer for 4 points. Okay. So but everyone is using the same rule, so we don't have a kind of discrimination or inequality there. Okay. So the 4 things that I ask you to pick the definitions for the 4 terms on the left. Okay, test case, test run, test oracle, and test point. Okay, so what is a test case? Test case is some static things enable you to do the test. Okay, so we look at this test case. There's a D that a static object defining what test to perform. Okay, so that's a test case. Okay, and a test run is basically a dynamic entity of something. You run the thing. Okay, so it's number 2 test run is a dynamic instance of test execution. So it's you execute something, or sometimes that you get this from actual execution. Test oracle is a way to check the input, output, and the result, whether the output is expected or not. Okay, so the better way here is that you look at a way to check test output and the results. Okay, and the test point is a combination of tests. It's basically a select point of your input values. Okay, so that essentially is a combination of the test input values. So if you have input variables of n-dimensional space, and then each of those variables will have a value, so that you get a test point there. Okay, so that's the answer there. Okay, so looks like 4 questions, but they are kind of very straightforward. So that if you know the answer to a couple of them, you are more likely to not to miss the other two either. Yes.
Can you give an example of a test case? I'm kind of confused what the definition actually means.
Okay. A test case, in a sense, is a little bit more detailed description about what to test, what you will be testing. Okay. So, for example, that when we do the boundary testing, okay, when we do the boundary testing, we have those extreme point combination, weak 1 by 1, weak 1 by 2. Those weak 1 by 1, for example, n by 1 test cases, those points, each of that points, you say that is a test case. Okay. You say I will use this one to do that. Okay. So it's basically what that says is that I have this program and I have this input and this is what I test. I test this on point. Okay. Yeah. So in a sense, in this case, the test case and the test point is related, so that you select an object and the test point that is the test case. Okay. And in some other cases, some of test cases are not as well specified as this. Okay. So we had those some of those partitions and things. So we say you test something to be true, something to be false. Okay. A test case, you maybe select some of the things and then make sure that this thing is true. Okay. So. Okay, so those are the multiple choice questions. Okay, with the short answer questions, we had a little bit more fun because they are not completely in black and white, and sometimes when you answer something true or false, you can get points. Either you answer true or you answer false, as long as your argument makes sense. Okay, so the second set of the questions, the testing QA and SQE, so kind of all kinds of short discussion kind of things. The first one of this second set said true or false. BBT and the UBST are the same because both are based on customer users' perspective. Well, the statement itself is false, because when you say BBT and the UBST are the same, unless they are the different names for the same thing, they're not the same. Okay. For example, if I say BBT and the functional testing, it is the same, because that's just two different names. Black box testing and the functional testing is the same. Okay, but the usage-based statistical testing is not the same as black box testing. Okay, so for example, that going back to our testing techniques that we have covered so far. For example, when you look at black box testing, you may have partitions. Okay, partitions based on external input output. Okay, so that's the pure black box testing. But when you do usage-based testing, you're not just looking at the partitions, but you're also looking at which partition is more likely to be selected. Okay, so it's not the same. Although they are both based on the customer user's perspective. That's true. That part is true, but the part that claim them to be the same is not true. Okay, so essentially what you need to do here is that say it's a false, and then why it's a false, and so for example, in my case, I gave you the example of the basic partition testing, and that's a black box testing, which is different from the usage-based testing with multi-operational profile. You have the partition and the probabilities. Okay. The next one, if you said it's true and gave some argument, then you probably, I don't think you get all 5 points taken away. Yeah, I would have looked at your argument, and if it makes some sense, you get some partial credit. So more sense you make, the more partial credit you get. Okay, but so it's not like if you answer true false in the wrong direction, you don't get any points at all. Okay. The next one, what is the primary purpose of process improvement in terms of defect prevention, removal, or containment? That's our classification, as all the QA divided into defect, either defect prevention or removal or containment. Okay, and as we emphasized before, process improvement is really focused on defect prevention. Okay, so that's what we talked about in class, and also it's discussed a lot in the chapter on process improvement. What about fault tolerance? Well, fault tolerance is classified as a defect containment. Okay, so with fault tolerance and the safety assurance, they are both in the containment. In this case, is that fault tolerance, you are not preventing the injection of defect into the system. Okay, you are not really removing them, although you may remove some of the things if you have very sophisticated kind of facilities, but generally we don't remove fault there, and we are trying to try to contain them so that their impact will not be as bad. Okay, so that's the main purpose. So fault tolerance is really about defect containment. Okay, I think a number of people made some mistake because they had trouble really interpreting this question. Is what is this about? So I'm basically asking you to give the classification in terms of this defect prevention. Is it a defect prevention? Is it a defect removal? Is it a defect containment? And so some people end up describing what is the process improvement, what is the fault tolerance. If you did that, you at least get some partial credit. Okay, you didn't answer the questions directly, but at least you know something about what is defect prevention, process improvement, and you know something about what is the fault tolerance. Okay. Yes.
What is process improvement? What is it?
Oh, process improvement. We did that with in the defect prevention chapter. Okay. So essentially, what we do there is that it's more along the line of the SEI CMM, okay, Software Engineering Institute capability maturity model. So they are looking at the software processes and how do you improve the software development and maintenance processes so that you can have fewer defects injected into the system, and then later on, actually, you can also have a good testing and other processes. You have a comment there? Okay.
How about achieving other non-functional requirements like performance?
Performance, you mean the process improvement part?
Yeah, as part of process improvement, we are trying to achieve all of the quality goals like
Yes, yes.
So it might include some usability.
You do. Yeah, you do kind of. That's why there are SEI people and a lot of people related to defense, they kind of focus a lot on process improvement. So because they say this is something that kind of had a very widespread impact on the overall software development, software product, and the thing. But the question here is asking them to, in terms of the defect prevention, the removal and containment. Yeah, this question is in terms of this. Yeah. So, yeah, that's the context of the question. Okay. The last one of this set said that when a QA strategy is formulated, should we select a single QA technique? Why or why not? This one, I think almost nobody said that we should select one, single one. Actually, I take that back. I think maybe a couple of people said that you should select one, but generally the expectation is that we talked about different QA techniques is really each one has their own individual strengths and weaknesses. So for the overall product development, typically you need to select several of them. Okay, so it's typically it's not a good idea to select a single one. Yes?
And what do you mean by when the QA strategy is formulated?
Yeah, when we were talking about you formulate a QA strategy, so you want to do QA, what kind of QA you want to do. That's when the strategy is formulated. And actually, that's part of the SQE process, the planning stage, the quality planning. Okay, quality planning, you have the goal setting, strategy formulation, and you have there some kind of monitoring facilities, measurement and monitoring. Okay, so let me move on to the next one. Next set is about testing. Okay, again there are a number of questions about testing. Okay, the first one said briefly discuss the similarities and differences between UBST with MUSA and BT. Okay, so it's a UBST with MUSA OP is one, and the BT is another one. So in terms of the natural language used here, there is some ambiguity. So UBST with Musa and with the BT, but the BT is not used with the UBST. So if you kind of have some context information, some domain knowledge, you should be able to parse this one as UBST with Musa OP is one technique. Okay, boundary testing is another technique. So ask you to compare the similarities and the differences. Okay, so the expected answer for this one is that when you look at the similarities, so they are both based on the underlying structure is a partition. Okay, doesn't matter you're doing the boundary testing, you're doing the UBST with Musa OP, the underlying structure is a partition. Okay, so with the Musa, that you have each of the individual operations, so that's a partition. Okay, and with boundary testing, so then you look at the different domains and they share some boundaries. So those different domains are forming a partition. Okay, so they all derived from some basic partitions. Okay, so that's their similarities. And then the differences is how you do test. Okay, how you use the information to do the test. Okay, and what kind of additional information you have. So boundary testing, you just focus on the boundary problems. And UBST, you focus on the usage. If you have more usage, you test more, so that because it has a higher impact on the reliability of the product. Okay. And sometimes people say, oh, I want to say a few more similarities. Yeah, there are some similarities. They are both kind of are away from the basic partition with the uniform sampling. That's one of their similarities. So they are both different from the uniform sampling for the partition, and they both focus on some kind of likely defects. Okay, and so if you want to add those things, that's fine. But the basic thing is that they are based on some similar underlying models, but their main differences is the way it's modeled, the information collected and used in testing. Okay. The next one, how would you solve the test sensitization and oracle problems for the above? Okay, so you have to know what is the test sensitization, and you have to know what is the test oracle. Test sensitization is basically you try to select the input values to make you realize what you want to test. Okay. And the test oracle is you have to have a way to check the result to see it is expected or unexpected, it's a success or it's a failure. Okay, so for example, for the UBST with the Musa operational profile, sensitization is fairly easy because that when you did that operation, you already selected the operation, so you just essentially you just select from the operational profile. Okay, and sometimes you probably need to do a little bit more refinement. With boundary testing, test sensitization is you select those points. Okay, and with boundary testing, you select those points, and then a lot of boundary testing strategies, we already kind of zoom in on the specific selection of the points, so you can use that to do your sensitization. Okay, oracle problem for the Musa operational profile. We don't have a really ready-made solution, so it's a kind of a general solution to the oracle problem. What is you observe the external behavior and see if it's expected or not. Okay, so for the boundary testing, we essentially have a simplified oracle assumption. Remember we always say, okay, you are receiving the A kind of processing or B kind of processing, A kind of treatment or B kind of treatment when you are on the boundary or off the boundary and those kind of things. So you do have the oracle problem is in terms of what kind of processing, what kind of function were executed or carried out. Okay. The last one of this set. Can the above testing be automated? Briefly justify your answer. Okay. So the basic understanding here is that, of course, when we look at the testing automation, there are always some opportunities for automation, but generally we cannot expect the fully automated the testing. Okay. So similar to this Musa OP and also the boundary testing. You can automate something, but you cannot automate the whole thing. So what I expect you to do is to analyze what part of this it can be automated, what part of this cannot be automated. Okay, for example, with Musa's operational profile, once you have the operational profile, the test execution you can do a lot of test automation with. Okay, and with the boundary testing, you can do some of the test execution automation. And the information collection, Musa operational profile, you can do a little bit, okay, probably not too much, okay. And with the boundary testing, for the small problems, probably you can analyze some boundary with some automation. But for the general problems, will still be hard to automate everything. Okay, so you can kind of break down some of the individual things, and so as long as your answer makes sense, you'll get, I guess, most of the points there. Okay, so I was looking for some important points you mentioned there. The important thing here is that, yes, some part can be automated, but not the whole thing. Okay, and then you can zoom in, give a kind of some citation example about the part of the things that you think can be automated. That would be nice. Okay. Next one, okay, it's about the simple coverage and usage testing. Okay, the first part say an OS manages various system resources, including computing, storage, networking, communication, facilities, etc., and provides support for different users, including human users as well as the other software, hardware, and systems to accomplish their tasks, building your models and the test cases to test this program, use diagrams, decision trees, etc., to make your answers clear. Okay, this one is a kind of a typical case of a kind of a partition and usage kind of things. So when you look at this, the most obvious choice look here is that you look at this. You see here that this OS manages this and that. Okay, and to provide support for this and this. Okay, so in a sense, you have kind of like two variables. Okay, and you can think of the cross product of those two variables and things. So you can think of this as a table or product, cross product, or some kind of partition. Okay, so the first part is really some form of a partition. The partition can be a cross product in the form of a table, or maybe as a decision tree. Okay, that's the kind of a more natural kind of things that you can say. For example, you can looking at for different users, and then what kind of things you are doing, and then what kind of things are managed by the system. Okay, and so generally, my expectation is that you have some kind of tree or some kind of table to have some partitions. Okay, so this is a partition, and then how exactly you do it is really up to you. So that's the creative part, and essentially, I'm not constraining you to one particular thing, but anything that makes sense, you get some point. And if I think it makes good sense, you get the full credit. Okay, at least it makes some sense, you get at least a partial credit. Okay. The second part of this, if you have a system logs that contain detailed information about the current version of the OS, okay. Can you enhance your existing testing technique above to ensure the quality of the next version of your OS? You may make up some numbers to illustrate your solution. So this one is a typical case is that now you do have some information about the usage of your system. Okay, if you have the usage of the system, you say you want to ensure the quality of your next release of your operating system. So the things that is important to users, used very often to the users, should be tested more often as well. Okay, so this is a kind of classical situation where usage-based testing can be applicable. Okay, so depending on what you did in the previous part, you can enhance your model differently. So if you use the cross-product tables, then essentially what you have there is that your cross-product table, each of the cell in the table will need to be associated with some probability. Okay, in a sense that you will get your flat Musa operational profile Okay, and if you use some kind of decision trees, some kind of multi-hierarchical list or decision trees like that, then it's a kind of where you can associate some probability with those decision nodes that when you select between different things that you can associate the probability with it. Okay, so depends on how you did it in the first part, you can enhance it with some probability and doing the usage-based testing. So that's this part. Okay. The last one, last question, question number 5, input domain boundary testing. For web applications, the primary quality attributes are reliability, usability, and security. Okay, so given several such software, if they are all met their security goals, so I holding security single, taking the security out of the question. Okay, the recommendations will be based on a comprehensive score S in the form of S equal to alpha R plus beta U. Okay, so R and U are the reliability and the usability measure. So essentially, you say reliability and usability are both important to us. But how much more important is reliability than usability, or how much more important is usability than reliability is depending on that alpha and beta values. So if you have larger alpha values, so you put more weight on reliability. You have a larger beta value, so you put more weight on their usability. Okay, so that's the thing. Then I say where R is this and U is this. Okay, if S greater than KU, the software will be recommended. If S is less than KL, the software will not be recommended. For cases in between, the recommendation will be determined by other factors. Okay, so essentially, this is a clear case of the kind of a boundary. So you have this S greater than KU and S less than KL. So that's actually the upper bound and the lower bound. Okay, and so if S is greater than or some upper bound threshold, then it's good, very good software. Okay, and we'll recommend them. And if S is lower than some kind of very low value, so it's a very bad software in both reliability and usability. So we don't want to recommend them. And since in between is in the gray area, so we need to make some further investigation. Okay, so if you look at this question, basically we are looking at the S score. S score, S greater than K of U is a 1, and S less than K of L is another 1. And then you have the S less than equal to KU and greater than equal to the KL. Okay, so that's, you can call it A, B, and C. So you have 3 parts. That's your partition. Okay, but the thing is that some people start to look at, oh, okay, I can just do the testing on S. Okay, but S is really not the input variable for your testing. Okay, so if you did a testing on S, you get some partial credit. Okay, so you model this as a one-dimensional problem. One-dimensional problem is basically this is the S value. Okay, you can say, okay, here is a KL, and here is a KU. So you have this is A. I have this okay, greater than A, B, and C here. So this one is here, this one is here, and this one here. So this is a one-dimensional solution to it. But you are not really looking at the original input for this problem. So it's kind of only a partial solution. And so if you did this one, you get some partial credit. Okay. And then, of course, if you do this, I ask you to do the n by 1 EPC. EPC is under minimal max over for this. So under minimal is immaterial for this part. That max over, and under minimal max over, under minimal max over, goes to infinity here. So that's the EPC for this 1D thing, and then you can look at the 1 by 1 n by 1 strategy. In this case, 1 by 1 and 1 by 1 is the same because it's one-dimensional. Okay, so for example, if we take a B here, then we will be having this pair of test points, and that will be our n by 1 strategy. Okay, but this is a kind of a simplified thing so that you are not working on the original problem with the reliability and usability. So the actual thing is that I'm asking you to work on the reliability and the usability dimension. Okay, so if you think, let me go over this way a little bit. Well, you can, for example, you can call this reliability, this usability. Okay, so then what is alpha r plus beta u? It's basically a line here. Equal to something is a line here. Okay, so for example, that you may have something like this. Okay, and something like this. Okay, so this is a S equal to, or you say alpha r plus beta u equal to the KL. This line is defined by alpha r plus beta u equal to K up. Okay, so this is essentially what you have there. Okay, and then this is A, this is B, this is C, right? Okay, and because we also have the boundary conditions on the R's and the U's. Okay, and so actually, when I did this one, I didn't consider R's and U's the other boundary conditions. So it's really only very small part of the partial solution. Okay, and then here we looking at the things will be here. R and U will be both be 0 or above. Okay, and so R is actually between 0 and 1. Okay, so this is 1. You cannot go over here. So you have an absolute boundary here as well. And you may have some boundary over there. Okay, so that's the A, B, and C. With this A, B, and C, then you can do the EPC and so for example, when we consider B, what will be the EPC for B? The lowest U is here. The lowest R is here. The highest U is here. Highest R is here. So for the EPC for the so for B, okay, then let's look at the focus on B, and you can do the same for the other things. Okay, focus on B, then what you have here is the extreme point on the R dimension is here. On this minimal, this is the max. Okay, on the U dimension, this is minimal, this is max. So what you end up is something like this one here. You get points here, here, and here. So those are your EPC points. Okay. As we can see here, the EPC point is not very effective because it's not testing any of the boundaries between A, B, and C, except here test some of the corner points, but completely missed this one, this part. So it's not very effective, and this one is completely outside of the B. Okay. So that's the EPC for when we focus on the B, the B region. Okay. And then what will be the 1 by 1, the n by 1 strategy? Okay, 1 by 1, n by 1 strategy would be, so n by 1 should be 2 on and 1 off, because B is closed, A is open, and C is open with respect to this boundary. So we need to select the off point here. And similarly, we need to select the on point this way and the off point this way. Okay, so that's the kind of expected answer for this question. Okay, of course, if you did this thing, that is a kind of simplified problem and not considering some other additional information. What's the input variable and things, so you get some partial credit. Okay, so I think a number of people actually did the 1D solution, either on this one or on the R alone or on the U alone. you get a little bit of partial credit, but that's not really a good solution to this. This is kind of the expected modeling and the solution, and then you may, for completeness purposes, you may need to include this one and this, the upper bound, and for the U and for R as well. Okay. Yes.
I think the off point should be in the B region.
No, this is here. Look here. Is A region is S greater than. So the off point will always be opposite to the on point. The on point is receiving B processing. See here.
But if we are testing whether we should recommend this recommended system. So the boundary is between A and B, right? So if it's over the A side, it's recommended.
Yeah.
So if it's not recommended, so if the not recommended side should be over the B region.
No. You see, when it's on the boundary, it's not recommended. When it's not, it's on the boundary, it is not determined. Okay. So it's recommended, not undeterministic. Okay. Further consideration. Okay. Recommended versus further consideration. Okay. Yeah. So this is actually, you see in some of the books, they talking about whether you look at the off point, which side should be in and the things. But the basic rule of thumb is that the off point will receive different processing than the on point. So you can do the compare and contrast. That's the easiest way to look at this selection. Okay, so guess that's all we have about the midterm exam. Okay, and so let's take a break now, and then when we come back, I'll try to finish up on the Markov operational profile for UBS. Okay. I think we are missing some of those charts. Break for a minute. Oh, it's over here. Okay, good. Thank you. I haven't got time to go back to look at your thing again because I don't remember exactly what you Yeah, it's probably has a little bit more to do with security than with the.
Yeah, that's my background, so I don't have a lot of software.
Yeah, you need to focus on the test.
Rather than that's probably wrong.
Yeah, so if something else like static analysis or something like, and just find the code base to just scan the code or something, because my issue is.
No, the thing is that as we said, the project assignment, you are expected to by some of the So just using existing static analysis is not part of the things that we discussed here.
Okay.
So you have to kind of pick something that you can apply some of our
Okay. I guess that's my problem. Okay. So like
Yeah, well, I had actually in the past I had several people had doing the security program, and then they naturally they want to hide it. But the thing is, the testing process have to do some testing.
Right.
Yeah, and even if you do security testing, you have to apply some of the basic classical testing techniques. In security, there are lots of kind of boundary values, policies, and other things. So
Yeah, but that's more like for code-based type testing and not having like, I guess the coding background, like code like constantly changing around, you know, because.
Yeah, I'm not getting paid enough for this, man.
Because I'm
I
trying to
quit.
work professional time, you can just take your code and whatever.
I got money for you.
then you maybe sometimes actually one of the things that we consider is
If you really want it,
you may
you gotta pay me
look
some
at
more
the
gratuity or tip.
Pardon?
I mean, if you really want the answers,
kind of observe.
No, just give us the questions. I'm just kidding. It's a last 2 chapters, right?
wait, this is 1022, right? So 4 chapters, two chapters.
If I'm doing like.
But
we already did 9 and 10.
And last
You still have to collect some data on something, that's the problem.
I took this.
Yes, I want last 2 chapters.
Okay.
So the basic thing is that you still have to,
Send it.
no matter what you do, you need to apply some of the techniques that we discussed in class
Okay,
to some problem that you.
okay,
You say 66?
all right, okay, just gotta think about it.
Yeah, think of some more, and then 66 you have some.
Oh, I don't believe you. Maybe the 90?
No. That's she got 9.
There's a question.
I only see the 93.
Uh-huh.
1 minus 1.
I thought that was.
3.4.
Oh, same thing I did. Everyone did a box. People like, no, there's no
I never did.
We think that's
I wouldn't have.
Something like that.
But no,
I assume.
No, I didn't think so. I mean, that's what you do.
So maybe I got the error from
I didn't work you. Oh, man, don't ask me that. I haven't started. It's really long. I will start.
Yeah. I guess that's the point, that's the from here.
You don't like how it's the last one.
Yeah.
It's like, just
That's not the, yeah. So I think maybe I marked out. Maybe I marked them mentally and then added them up and so that's what, that's the main point. That's 1, 2, 3, 4, and 4 and another 3.
Okay.
Yeah. Let me mark it for confusing. Yeah, I think maybe I just added on the spot. So.
The last one.
And that one, strategy.
You're passing this work.
And that one, yeah, and that one strategy. Yeah, and that one strategy is based on the number of countries. So. Oh, 3. So it's
That's like yes or no.
yeah,
You
it's
can't
an
get
MB
like
plus 1.
it's either yes or no.
So for each, actually, not the plus 1, the plus 1 is to be inside the parentheses. It's an n plus 1 package. Yeah, because you have n on and 1 off for each boundary.
No, one is
That's the
3 points. This is 3 points. And that is 1 point.
Oh yeah, you
one by one.
1 by 1.
Yeah, that's the 2 week.
Okay, so
Yeah.
this is your 6 points that can be tested.
In this case, yeah, because it's two-dimensional. Two-dimensional, so n is 2 plus 1 and 3 times 2.
Okay, so this one.
N plus 1 times b. Then plus 1.
And this is in this case, right?
Yeah. Two-dimensional, yeah.
So how is operation?
Two boundaries, one upper, one lower.
The stuff that I thought I did,
But I think
good
that
on
this
it.
parameter
It's
is
like
something
they were
surrounding.
Yeah, I know.
if that makes any
That's
sense.
not used in the textbook. It just says it.
Oh, okay. I thought I put it down. Let me check.
Homework 15 and more than 25.
It's like right around the corner. I didn't realize this. Looking when I started looking at the summary, they really expect you to be done by the time you get your summary done.
I'll just give you my laptop for you just write down the notes on it. After the class. Or next minute. I got a snack. Can you text me? I don't know. I texted you
Huh?
like a bunch of times. I didn't text you this time. Try to text me. If not, then
Right, but
oh yeah, it's mandatory.
so it doesn't matter, right? But you
Oh,
said
yeah, you have plus 1 times.
If you're in 7 hours,
That's the 3 times.
close to 25%.
6. The plus 1 is serial. That one we all.
For us, everything is
Yeah.
required.
even the summary,
It's only for undergrad.
your presentation is going to be longer, I think. No?
Doesn't necessarily stop.
About 15 minutes. Yeah. Yes.
So, and we were just telling him that he said the project summary is due for undergrad and grad.
No, undergrad, they are not required to do that. No, they only submit a report.
Oh, for us, we need to do everything.
Yeah. Graduate students, you have to do everything.
Your presentation, then the
If you are giving a presentation, you don't have to do the summary. Right, but the summary you have a fixed deadline. Presentation is scheduled.
Can I change mine?
Yeah, it's up to you. Yeah.
Oh, okay. Hopefully I can get it done. That's fine.
I try to have a schedule.
Number 847 in there.
All right. So I understand. Are you undergrad?
You want?
You doing the presentation? What are you doing? I think I might do the presentation. Because that's probably.
What do you need in 1 year?
Yeah. I remember you mentioned a lot. Yeah.
Like put on the slide, you mentioned that you have 50 cases. So I'm wondering like when you want to do this cases, want to verify for testing technique or can I do it like testing?
Okay.
It's up to you. It's a custom lower bound. Yeah, lower bound is something like, maybe the reasonable.
Especially since we gotta do yeah, so, yeah. I thought I had a presentation for this. I didn't say really, I was going to smile. Well, I'm thinking, I'm like, I don't know.
and I lost all my files.
Just now?
Yeah, I think they changed the computer or something, and so I think is this all-in-one? I think yeah, that's the all-in-one, and so I don't have my files anymore. Need to
Construction happening everywhere.
For us, this is the main. Just distribute who is and pass on token. So through him. Solution for your person, don't worry. I got questions as well, negotiate.
Group partner like that?
Thing is, what he's teaching.
not loading my slide.
Oh, yeah. You wanna go there and watch it?
Oh yeah, yeah. It's just slow.
This is my future. Judge. See, I got all the breakdowns and everything.
Right, how much have you read?
This is everything after that. That's why I wanted you to send me the link of all the videos. See, I was serious. I was talking. With you, I was talking about this. Next time, he said, next time you work with different, I'm not taking different.
You guys wanna
That's why we gave you a lot of.
She's very fun. You know what? Nikuna wife will be very fun. Trust me.
That's what usually happens. You always get the opposite.
I got a most serious wife ever person I've seen in my life.
Same.
No, that's a different life.
Yeah,
It's totally different life.
You haven't seen me like undergraduate school. After, like, this is different.
You can imagine how I was in this.
I don't even remember.
I mean, I was,
When
I was
did you
never
graduate?
when did you graduate?
Which year you graduated?
It's funny watching you.
Okay, let's go back to our class. Sorry about the slight delay because we had upgraded the computer and I lost all my files, and so I have to load them up, and then we can discuss their things. Okay, so let me switch over. I have them now. Their presentation PC. Okay. So yeah, so this is the new one, and somehow on the Internet Explorer, when I load the PDF file, it kind of got freeze on me. So in the last class, we start to look at the finite state machines, okay? And we talked about the basic concept about the finite state machines and the representation and how to use the finite state machines, how to construct the finite state machines and use them for testing purposes, okay? So we did all that, okay? And then we looked at it toward the end of that class. We said, okay, let's have a kind of an honest assessment about the finite state machines and how well they are doing things. Okay, so we looked at some of the limitations with finite state machines. So one of the most obvious kind of a limitation is that we do have the state explosion problem. Okay. And so when you have a lot of states and a lot of transitions, this one will become very hard to manage and use for testing purposes. Okay, so we said, well, maybe we can do something by trim down the states by doing hierarchical models, or sometimes by looking at the sum of states. Maybe if you do purely doing hierarchical models, you may be missing some of the important things. Okay, because some part of the things may be very important. You should test more, and when you do the hierarchical model, it's getting kind of hidden in some lower level corners, and so you end up maybe not testing it enough. Okay, so that's one of the problems, one of the dangers of using hierarchical models, because there are certain things that's important, but hidden deep in some place, and then you won't be able to discover. So what we can do in this kind of situations is that to take a look of the finite state machine and then look at how often those different states are visited by the customers or users. Okay. And so how often they are going through those states, okay? And how often they follow certain transitions, okay? So if we have that kind of information, then we can do kind of usage-based testing similar in the way what we did with the Musa's operational profiles, where we look at the partitions. Some partitions get used more often, then we can use that partition, and then some other partitions we use less often. We can kind of skip them when we first doing the important part of the partitions. Okay, so we can do the same thing, but it turns out, let me see if I still have a few of the finite state machine examples here in my collection. No, for this charts we draw before, okay, and let me see if we have some of the things, okay. Okay, yeah, we have a couple of things that we can talk about here. Yeah, so for example, that we may have something like this, okay? When we were talking about the that's camera here, okay? So when we were talking about the idea of Musa's operational profiles, we started from here. We said that we have those partitions, but some of the partitions are used more often than others, so we can reflect that in some models and then test accordingly, okay? Similarly, with finite state machines, say if we have a finite state machine like this, we can say, okay, how often do you go through each individual states before you finish or going over some of the times, okay? So we can kind of want to have some information about the relative frequencies of visit to those different places, okay? But it turned out to be with the finite state machines, we have some nice properties about this. It turns out that, well, as long as you specify the transition probabilities, you can calculate the state probabilities. Okay, so because if you say you always start here, when you start here, you can go here, and then you come here, and you can go back here, and go this way. So in this case, what we have here is that from A, you don't have a choice. You only go this way, right? From B, you don't have a choice. You only go this way. And from C, you do have a choice, okay? So depending on the choice, actually will reflect the things about how often you are going to do this and that, okay? So for example, if I have something here, have 9, 9, 9, 9, something like here, then what that says is that when I come here, I almost always finish up here. I almost never go back to here or here, okay? But what if I have 1/3, 1/3, and 1/3 probability? Then I'm equally likely to go here, or go back here, or go back here. So if I have 1/3, 1/3, 1/3 probability, then what's the probability of I will be going to A or going back to B? And actually, in this case, I'm going back to B more often than going to A, right? Because 1/3 probability are going back to B, 1/3 are going back to A, and A will going to B also, right? So actually, B will be visited more frequently than A because you are in this little loop as well as in this big loop here, okay? So the thing is that when we try to specify how likely we are going to go visit some states and how likely we are going to go follow some transition, with the nice property with the finite state machines is that as long as we can specify the probabilities for the transitions, we can calculate the probabilities about the states, okay? And so that's why we, when you look at the Markov operational profiles, when you use the usage-based testing, collect some usage information. Typically, you just need to collect the information about the transitions. Okay. Of course, if you can directly collect some information about how often I'm in A, how often I'm in B, how often I'm in C, and how often I'm in D, I can do that as well. Okay. But the basic requirement is that you need to absolutely minimal information is that you need to collect the information about the transitions, and then we can make calculations about how often you are going to be in B, in C, in A, and in D, and so on and so forth. Okay, and also when you look at this kind of Markov chains, we have a different type of the kind of machines or Markov chains. Say, for example, with something like this, if this one is your initial state, this one is your final state, okay? So no matter how you run this one, eventually you will go into here and never come out, right? So this one in the so-called Markov chain theory, okay, or the stochastic process theory, this is called an absorbing chain. So this one will be absorbing the things. Eventually, everything will end up here, and that's the end, okay, of the end of the universe, end of this Markov chain, end of this finite state machine, okay. But there are other cases where you don't have this kind of thing. Say, for example, just imagine we don't have this part. We just have this part. If we just have this part without this part, then what happens is that this one will go on forever. Once you start, will go on forever. Okay? So this kind of a thing is called the recurrent chain. Okay? And that kind of thing with some sinks that eventually everything will go in there is called the absorbing chain. Okay? And for those kind of different chains that there will be different kind of theoretical foundations for calculating this and that and all kind of things. But the basic idea we have here is that now we want to capture some usage information to be used for testing with the model of finite state machine. Okay, so essentially what we are trying to do here is that if we want to do a little bit more on the things, test, say for example, with here, if I want to test this one more, then if this one is used more, then I test it more. And then particularly, for example, if I have something like a 0.1 here, and here 0.8 here, and 0.1 here. Then I know the relative importance of going back this way or going this way, okay? Or maybe I have 0.89, the 0.1 here. So make it more unbalanced. And then in this case, I don't want to really test this one the same as testing this one, okay? So we want to kind of capture some information about their actual usage in our finance state machine by enhancing our kind of finance state machine to with some probability information that captures the usage. Okay, so essentially what I'm saying here is that you can see here is with this finance state machine, we're saying here if you are here, if you have this probability distribution. What I'm saying here is that it doesn't matter how you get here. As long as you are here, you are following this probability distribution. Okay? So that's a simplification of some of the real life examples. In the real life, it's probably you're looking at what's the condition and how likely under some conditions I go this way, some conditions I go this, some conditions I go that way. Okay? But here we can simplify this a little bit and say, as long as I'm here, I'm looking at what's the probability of going this way, going the next way, going the third way, okay? And that gives us information about how likely the users and the customers are going to be following those different transitions, and then we can propose to test things accordingly, okay? And that simplification is makes this comes to this name called the Markov chain, because this is called the Markov chain because that's first studied by a statistician, a Russian statistician called Markov, and he said that there are a lot of situations you can simplify things and without looking back at the history, just looking at the current state, and then you can decide what's the next move. In a lot of the situations. So that's a simplification, make it much easier to manage a lot of things and model things. And sometimes it's not such a big stretch from the reality. So has been used and studied and used ever since. And it's the most commonly used kind of those stochastic processes in the mathematics and in statistics. Okay, so people use that, and so we can make use of those kind of information to help us with testing. Okay, so what we can do next is to look at the concept about the Markov chains and look at how do you build the Markov chains, how do you use the Markov chains for test, and looking at some case studies of using this thing. But the idea is kind of simple. That's a kind of parallel to the idea of what we did with from Musa's operational profile. We derive from the basic partitions. So in a sense, you can think of this picture that where we get to this place. Okay, so the picture is like this. If you think of this one, we had the so, for example, we have the partitions and PT, partition test. Okay, so partition test, and we can add probability, probabilistic usage information. Okay, we add a probabilistic usage information. Okay. And then we got to the Musa OP, okay, inside operational profile, okay. And then you can look at it here. We have the finite state machines. You add the similar kind of thing, probabilities, okay. You get the Markov chain, okay. Actually, along this thing, you had the parallel of this thing. You add a probability to become this thing. And actually, you can go down. You can add structure. Okay, you have the partitions. If you add the structure and model some of things, you get the finite state machine. Okay, so that actually later on we will come back to this chart here. Is that when we are doing the Markov chain, because it has an underlying finite state machine and has a probability, so we kind of can do this in 2 steps, looking at the finite state machine and then looking at the probability. And so looking at the structure and then looking at the probability, then we got the Markov chain. Okay, and so sometimes then we can look at this thing. Can we convert something between the Markov chain and the Musa operational profile? There is also some possibilities of doing some of the conversions here, and you can collapse some of the things into the partitions in the finite state machines and as well. So we can look at this kind of information about how do you relate one UBST. So on this side, we have a UBST. And on this side, we have a coverage-based testing. Okay. On this side, we do the usage-based testing once you add the probability information. And then for the UBST, we can either do the Musa operational profile or we can do the Markov chain. So those are the 2 primary UBST models. And towards the end of today's class, we'll be looking at a little bit more of the comparison and maybe some level of conversion between the Musa and the Markov operational profiles. Okay, so let's go back to the slides. We talked about the basic ideas a little bit, and now we can kind of look at some of the formal definitions and how we model those things. Okay, so the Markov operational profile. Okay, it's really we have some state transitions and the probabilities. Okay, so essentially we have the basic finite state machine, and then we add the probability to the state transitions. Okay, it can be attractive in interactive systems, the GUI, and many state transition types of things with uneven usage. Okay. And actually, one of the basic things, this is a kind of almost always the truth, is that you have this kind of so-called 80-20 rule observed in almost all the software systems and their usage. Okay, says that you have very uneven distributions of the things. 80% of defect comes from 20% of the functions of modules. 80% of time, people will use 20% of the functions or something like that. Okay, so it's very uneven, and because it's very uneven, when we test, we shouldn't test uniformly. That's the basic argument. Because it's uneven, if there is a problem, the problem impact is going to be uneven. Okay, so if we want to make sure it's reliable for the customers, users, and the reliability improvement in their perspective, then we need to test some other things more than the things that use less often. Okay, so we want to have this kind of thing, and it had some structure because of the underlying finite state machine. Okay, so it's a comparison. We had this comparison with the Musa operational profile. So this kind of basically you add the partitions, you add the probability, you're going to become Musa. With the finite state machines, you add the probability, you have the Markov OP. Okay, and so it helps us testing the important part, the part that is going to be used more often by your customers and users. Okay, and so the application of this models are similar to the Musa OP, but with more of a structure. Okay, and when you look at the test case generation with the Musa operational profile, generally we assume that when you go to the operational profiles, each operation can be uniquely identified, and then you say, I'm going to test this operation, you will be able to test this operation. With the Markov OP, it will be a little bit more complicated because you will still be going through a number of transitions. So just with the model itself is not giving you the test cases. Okay. So for example, that if I have this one, and I want to say that I want to test some kind of situations of from A to B to C to D. Okay, so I need to still have to go through this sequence and looking at the probability, how often I'm doing this. Okay, and actually in this case, this sequence is actually of low probability, but this sequence is actually of higher probability. You're going this way, and going back to A is of higher probability. If you are not looking at the complete execution sequence, you are just looking at a segment of 4, of maybe this 1, 2, 3, segment of 3 steps. 3 steps, this one, A, B, C, A, is more likely to be selected than A, B, C, D, or A, B, C, B, okay? Because this one has the highest probability here, okay? So if you say, okay, I want to test some 3-step operations of this system, then this one should be tested first, okay? So yeah, but then how do you do that? Is that you have to follow through the chain and calculate the probabilities, okay? So the calculation, the test cases, sensitization is not that trivial, okay? You have to go through a number of steps, okay? So the test case generation and the sensitization is not trivial. It will be a little bit more complicated, and actually that will be part of the things that when we talked about when you have the Markov chain, you want to use it, how do you use it? That will be a part of the discussion we will have in today's class, okay? And when you analyze the result, because we do have the Markov chain itself, and actually there are lots of theoretical foundations about the Markov chain analysis, okay? So we can do some analysis as well, in addition to just observations, okay? So that is actually, there's some added power to the Markov operational profile, okay? Actually, I need to go down a little bit, okay? So the background and the linkage we talked about is when we look at the basic concept is basically finite state machine. You add some probability through into the transitions. That's the Markov chain, okay? And historically, it had a lot of linkage to the clean room technology. Clean room technology was initially developed by Harlan Mills when he was working for IBM Federal Systems Division, okay? And so essentially the idea with the clean room technology is that they argued that the traditional waterfall process is not working too well in terms of producing high quality software. The clean room is that, in terms of the clean room technology, that you are trying to have a so-called clean room to develop the things so that you have less chance of defect injection through some kind of a formal inspection and verification, okay? And so you are supposed to be doing all those things, and you're not supposed to do testing all the time up front. But then when you have the whole system ready, then or in an incremental fashion, you can test the whole system from the customer point of view. When you test it from customer point of view, you need some usage profile. And so the usage profile and the operational profile is in the clean room technology, typically they work on those things that they say you need some kind of finite state machine with some probability. So that's their clean room connection, and some of their important papers on their Markov operational profile were the initial ones were all kind of associated with the people who worked on the clean room technology. Okay, so Whitaker and Thomason worked on this. Jesse Pora worked on this, and actually they were all involved in working with at least some of the senior members of those teams who worked with Harlan Mills and his Federal Systems Division on the clean room technology. Okay. Over the last few years, I think a little bit more than 10 years now at SMU, we have been working quite a bit on extending their Markov operational profiles into testing for various different applications. We worked on the Markov operational profile for telecommunication testing, for web testing, for cloud testing, And we established our own models called the UMM, Unified Markov Models. So it's really a collection of Markov operational profiles, but we organize them in a hierarchical structure. So I'll mention a little bit about that when we talk about the different testing there. Okay, and so this is an example that kind of follows through the example we had before about the operational profiles and the finite state machines. Okay, so this was our original finite state machine with that kind of state transition diagram for that cellular communication system. But now, in addition to the basic states and the transitions, we added some probability information. Okay, so whenever there's a choice, we need to add a probability information. Of course, when there's no choice, only one choice, okay, when only one choice, then the probability of making that choice is 1. Okay, so that's so we have this one, the probability of A to B, that's the only choice, so probability is 1. And this one from B, you can only go to C, that's 1. And then from C, you have a choice of go down to system access and go up to back to the mobile station initialization. Okay, so we have to look at how likely this thing happens. And so this set of numbers, actually, I got this set of numbers from Eric Lin, my colleague at the time, because he was very familiar with telecommunication systems. Okay, and worked extensively with the telecommunication systems, and so familiar with how often those kind of things. So essentially, what I did here is that I consulted expert opinion about how likely this one is going to happen, how likely this one is going to happen, how likely people are going to make this transition, make this choice. Okay, so that's the kind of remember with the Muser operational profile. We mentioned about when you collect the information to build the operational profile, we have 3 generic ways to obtain the information. One is the expert opinion. One is a customer survey. Okay. Another one is actual measurement. Okay. If you can get an actual measurement, that's typically that's the gold standard. Okay. But a lot of times you may not be able to get the actual measurement. Okay. So in that case, then you have to do a survey or ask your expert to give an estimate for that. Okay, so in this case, what I did is I asked the expert and I got those numbers. Okay, but then you can do the actual measurement and some kind of surveys and things. I don't know if I mentioned this. Actually, one of my PhD students is now working on precisely this problem because with this operational profile construction, you need to collect a lot of information. Okay, but if you think of it, remember the definition of operational profile from Muser's paper and in our book. Operational profile is the quantitative characterization of how a projected system is going to be used by your target customers. So you look at a new system, a new function, and they're going to go to the market, and you want to look at this one, the future usage. If you are doing measurement, you are not really looking at the future usage, right, of this version. But you typically, you do have some measurement of your older version, right? If you have a measurement from your older version, and you want to say, what's going to be the usage for my new version? The chances are they are going to be somewhat similar. Because since people rely more, well, people will rely more on in this new version as well. But you may have some new functions, okay? You may have corrected some old problems. You may have some new functions. And then all those things will affect the accuracy, the precision of the match between your old operational profile and your new usage. So one of my PhD students is now working on this thing and looking at, okay, how can I solve this problem by looking at some of the other artifacts, documents, other information sources that I have in my disposal from the development process. one of the such things is looking at the design documents. Okay, look at things, or I say I have some design documents indicating that this one will be replacing some of the existing functions. So then I would expect these things will be having the similar kind of usage. These new things will have similar kind of usage with the functions that they replace. Okay, so you can do some of those kind of reasoning, and then based on the old operational profile, you can make a projected estimate of the new operational profile. And then once you get the new measurement, you can validate whether your projection is correct or not. So that's a kind of a new approach to this operational profile development, and one of my PhD students is working on this. Okay. So this is the concept, and then the key thing here is that when you look at it, it's the outgoing links forms a probability distribution. From every node, all the outgoing links forms a probability distribution. Okay, so essentially I say all these probabilities, the Pij, they are between 0 and 1. And the sigma of Pij over j from any I, from any state, all the outgoing links will eventually go in somewhere. Okay, so all the outgoing links, their probability, when you add them up, they should be probability, the sigma or the summation of that should be 1. Okay, so that's basically the Markov operational profile. And notice here that we have this Pij. What Pij signals is that it is history independent. Doesn't matter how you get to here. As long as you are here, this is the probability distribution you will be following. Okay, so that's the so-called memoryless or Markovian property. Okay, formally stated is like this: if you have a history from different states, from you at time 0, you are at state 0, and then the state 1, state 2, up to state up to state n, and then you go into state n plus 1. So if you are at state n, you are in I. Okay, your stage A, your state is in I, and then next one you are in J. So it will be equivalent to you are in I going to J. Doesn't matter how you get there. So the whole history is summarized in that you are here. Okay, so that is in the literature, in the mathematics statistics literature. This is called a memoryless property or Markovian property. You don't have a memory of your past. All the past is actually, in a sense, all the past is summarized in your current state. So I only make my decision based on my current state. I don't go back to history to look at the history to make my decision what to do. And this what to do is probabilistic and only depends on my current state. Okay, and so this Markov chain is basically it's a history independent. Okay, and it's the most well-studied stochastic process. Okay, and there are lots of analytical and theoretical results with that, with a lot of applications. Okay, it has been used in all kinds of things. So, for example, that one other area that they use the Markov chain a lot is in system performance evaluation. Okay, system performance evaluation, you will look at the system and look at the network, look at the queuing, look at those things. They use Markov chains a lot. Okay, another area, completely unrelated area that use Markov chain a lot is data mining. Okay, in data mining, people use the Markov chain a lot. Okay, they use the hidden Markov chains and all kinds of different Markov chains, and then try to look at some of the decision problem can be modeled by a Markov chain. Okay, and so there are lots of results, and in the so-called UMM, it's that we do have here, we developed here at SMU over the last, I think, about 15 years or so. I think we started working on this, or maybe a little bit over 15 years when I was working with Eric, and we did something in 97, 98, so a little bit over 15 years ago. Okay, and most of our publications are actually within the last 10 years in this area. Okay, So essentially what we have here is that we combine the idea of hierarchical modeling with Markov chain. Okay? So when you have a Markov chain, and you can also have some lower level Markov chains for some higher level states. Okay? So this is an example of that UMM. So for example, this one is the high level Markov chain. But on here, this has a lot of complicated operations within it. So what we can do is here, we can combine the hierarchical modeling idea. They say, okay, I can expand this thing out. Okay, so expand this thing out, then what we have here is that we do have this thing expanded into this sub-states, okay, E1, E2, E3, E4, and E5, okay, and then they do the thing, there's a mobile station control on the traffic channel. You have traffic channel initialization, waiting for order, waiting for mobile station answers, and then do the conversation, and then after you finish with the conversation, you release, okay, and so go back to do other things. So this is another part of the Markov chain, which basically you have some of the high-level nodes in the Markov chain, which can be expanded into lower-level models. Okay, so when you have a number of those things in a hierarchy, we call this unified Markov models. Okay, so the UMM model, so we have here. We developed here at SMU, okay? And so this is a UMM example, okay? And so let me stop here, and then after that we will be doing the look at the Markov model construction and the usage, and some examples that so close this part off. Okay, so let's take our second break for now.
You can
mirroring management and locking.
Yeah, because Java is meant to also.
Java all that. That's the only reason why I would say that. Even though I might,
And because I'm performing in the skits also,
it's not that hard to transfer over, but I would see Java instead of C++ because of those minor, well, I wouldn't call them minor. But I think it's easier because you can also use clips and all that stuff. Yeah, if you know, like C++ or whatever.
Yeah, if you know one language, you can.
yeah,
Kind of is
Like, I had my friends, like,
must be alright.
two of my directors
college, and that's like 5 years. But you know, once you start, it's really, it's not that hard. Once you learn how to do your references in your classes, just, you know, it's really, and you always try to do this thing. Oh, I can do this. And then you start importing your classes so you can reference them.
Then when you learn about the scanners, wow, that's awesome. You can ask the user into anything. When I learned
It's like doing what scanner?
yeah, so if you ask the user, then respond based on the instruction.
No, I hadn't done it.
So this is what I'm doing. For example.
Oh, in here?
Yeah.
Wait, someone will do chapters, someone do slides, and someone will do course.
When you run the program,
all across, right?
I mean,
That's why we're splitting it, right?
Yeah.
So then we'll exchange it.
You guys have the next book, Size and Influence. You have it?
Which one?
The next one I have it.
Safari.
I have it.
Which one?
Influencing.
Oh, I don't know. Yeah, you were doing something, right?
No,
What, you decide, let me know what I want.
Okay, cool. Yeah, studying all
I don't mind.
And then,
No, seriously, I don't mind.
so we'll just assign after.
I didn't have a lot of comments on my so I can. What does it say?
Why? Last time you gave me two and you gave me one. No. No
And
cheating.
then, see, there, each year,
The youngest one here should get this.
Okay, you need to specify which techniques are used.
There's nothing to study.
No, don't worry about the slides. They're the chapter. So slides is really good.
Yeah.
You know you can combine all slides in one presentation, right?
She can only do it, but we can't do it.
Do you remember when you need to study for the
I will study all the chapter to combine it in one.
You know what chapter is what is on your first exam?
Oh, I know what you're doing. I know what you're doing.
there is what, 125, 960.
I remember this now.
I will go welcome you and the PCD was added to the queue so you can press the queue's content.
Okay, so 6, what was it?
6 questions.
Man, last time you did the same thing.
I actually know what you're talking about now.
You ever
I
get it
remember now. That was 2 years ago. I actually, once you started talking about, oh, and what, okay, I remember. You know what was the real bad thing is?
Yeah, it's
Yeah, so you have to have,
Oh man, that was a wrong
you
answer.
actually had a chocolate version manually doing it.
I guess we in the second part of the project we can do something. Now we don't need to worry about the queues and
Yeah, well, I don't think we did it.
so
Oh, that's where it is.
so there the queue is empty. Yeah, that's one part of the queue.
Okay, fine, okay. And you have to do a good job this technical. What a formal method as because
let you know Saturday morning or Sunday morning after the party. So I called and asked her.
You actually have to have it in or something to yeah.
If we suffer, let's suffer all. Yeah, that's what I said. 1 week you rest from research. It's 4 hours. Yeah. So 1 to 3, 6 to 10, 4 hours. Yeah. So per person. So 4 hours.
Start the test by 8:45, midnight to finish.
Yeah. Last one has to like last week is
Okay, let's go back to our class. Okay. Actually, I have a couple of things I want to talk a little bit about before we go ahead and wrap up this part on the Markov operational profiles and things. Okay. So I will talk about two things here. Okay. If you look at our class webpage, I have just posted homework number 3. Okay, so that is basically the things related to the last week and this week's content and related to chapter 10. Okay, and so essentially I ask you to problem 10.6 is ask you to construct a finance state machine. For something you're familiar with, typically a kind of manual-driven software you're familiar with, okay? And so when you construct that, I want you to include a kind of description and specification of the software you used for this problem, and then construct your finance machine. And then after that, I ask you to do 3 more parts of the things. So it's kind of like 4 questions, but all related to each other. So after you construct the finance machine, I want you to be comfortable with the other representation of your finance machine. So probably your first one is graphical, the state transitions and you draw. And then if you did that, you can convert it to some other things. So I ask you to convert your finance machine to another representation you did not use above. Okay, remember we have 3: graphical, tabular, and list. So if you use the graphical one, you can convert it to either tabular or list here. Okay, and actually, if you want to do both, so that's okay. Yeah, and then the next extension is that with your finance machine, if you do have some information about their usage, okay, and so can you kind of change this into their how do you capture this information in your model for usage-based testing? So basically, it's a kind of Markov OP question. Can you convert your finance machine into a Markov OP? And they'll have some discussion about how do you get those information and how do you convert this to the Markov OP. Okay. And the last one is actually the ones that we haven't talked about yet, but we will be. Is select a probability threshold and produce a flat OP from your Markov OP. Okay, so we'll talk about how to do those kind of things, but it's good to have an exercise. Okay, so you have this starting from today until next Monday to finish this homework assignment. Okay, and so you can receive some timely feedback on this, and then probably I will give you 1 more homework assignment, and then we'll be just focusing on the project and then the final exam. Okay. So that's homework number 3. I also want to talk a little bit about the project proposal. Okay. So we had some problem with the I actually had some trouble with the Blackboard, but then I actually worked with the Blackboard team, and they fixed the problem for me. And so there was a I don't know what happened. Is before I could save my comments, but I couldn't post my comments to you. Okay, so but now it's okay now, and so I finished reading all the project proposals and provided some feedback. In almost all of the proposals, I think they are generally on the right track, the right ideas, but need some more kind of attention to some specifics. Particularly, I think one common problem is that we have a kind of substantial number of students said that they are going to do black box testing, white box testing, that's it. Okay. That's not really enough, because we are talking about applying a number, at least 2 specific testing techniques on your things to be tested. So if you just said black box testing, white box testing, give me the what you are going to, what product you are going to test. I ask you to zoom in on some of the things. So be sure to zoom in on some of the things. 2 of the formal systematic testing techniques. Okay, and I remember I only, so the grade I posted there is because I need a numerical grade, so either 1 or 0, okay? So only one person got 0, everyone else got 1, okay? 1 doesn't mean that you are perfect, but please still pay attention to my feedback as you go on with your project, and make sure that you take care of that thing in the final report. Okay, so sometimes when I read the final report, I go back to my comments on your proposal and see if you addressed some of the specific things I mentioned in my feedback. Okay, only one student, I think that their proposal was kind of out of scope of this class, and so I asked the student to resubmit their proposal. But for the rest of you, you don't need to resubmit anything. Just take care of my feedback in your project and in the final report. Okay? Yes?
Are we limited to 2 testing techniques?
If you want to use 20, that's fine.
Okay. All right. I'm already at 4, so.
Yeah, that's okay. That's okay. Yeah, I only give you the lower bound. I'm not giving you the upper bound. Okay. But make sure you can finish something. So I don't want you to have start with too many things and couldn't finish. Okay. Yeah. Yeah, minimum is 2. Okay. Yeah, that's the lower bound. We only have a lower bound. We don't have an upper bound. Yeah, if you have a, yeah, it's up to you. Yeah. Yeah. It's a whatever. If you do 2, really do a very good job on 2, that's good enough. Yeah. But if you want to get a kind of a little bit more experience on different things, it's up to you. Sometimes when people focus on 1 and then kind of branch off to another 2, 3 briefly, that's okay too. Yeah. Yes.
How in depth do you expect these testing techniques to be? Because I did like a simple, test scenario, and I said, okay, that's my whole testing technique for that.
You need the specific test and the result. So okay. Yeah, so your test cases need to be derived from your model, okay. And then you need to actually execute those tests and then report the result, analyze the result, and analyze the result. Okay, that's why I said that it's more important to be complete than to be wide. Okay, because you will be building the model, get the test cases, run the test cases, analyze the result. That's a kind of a completeness with 2 techniques. If you start with 15 different techniques and if you don't finish testing them and don't analyze the result, that's not going to get you too far in the project in terms of the grade you receive. Okay. Yeah. So there are 2 complete is more important.
Use case and model and analysis.
Your model, you have to build your model, okay, and then you have test cases, and then you run the test cases, analyze the result, yeah. And of course, you need to write up the report also, yeah. Okay, and I guess that's any other questions about the project or other things? Okay, so let's go back to the slides. Okay, so we talked about the Markov chain, Markov operational profile construction. So the steps we kind of talked about the steps without formally listing them as the steps. Okay, so it's essentially what we had here. We said, okay, we look at these relationships with the mutual model construction. We need to get a partition, and we got a probability, and then we got the mutual operational profile. With the Markov operational profile, or Markov chain, or Markov OP, what we have here is that we need to get the along-the-line structure in the finite state machine. We need to add a probability, and then we got our Markov operational profile. Okay. So that is essentially the basic steps. And so with the mutual operational profile construction, we had remember we had those musa 1 and the musa 2 steps. That musa 1 is that you get the user customer profile, system mode, and then you have the functional profile and operational profile. And with musa 2, you kind of start with the defining your partitions and then adding the probabilities. Okay, Musa 2 is actually kind of more along this line. I mean, Musa 1 is a stepwise refinement. Musa 2, you said you have to identify the initiators, determine what kind of representation you want to take, and then you enumerate out all the operations. So you got the partitions. So the first 3 steps, you got all the partitions. And then you measure something and you normalize it, you get the probabilities. So the first 3 steps in Musa 2, you got the partition, okay, all the partitions. And the last 2 steps, you got the probabilities, okay. So with the Markov operational profile, you can get your finite state machine, and then you get your probability. How do you get your finite state machine? We talked about that last week, okay. And so that's the kind of the things that we already discussed. And with the transition probabilities, then essentially what we can do is that we can follow the kind of generic ways to obtain this. Okay, we say, okay, what are the ways to get those information? Okay, where to get the information is that we can use measurement, we can use some survey, we can use expert opinion. Okay, so as I mentioned that the examples we looked at so far with the IS-95 related Markov chains, I used expert opinion because I consulted my friend and colleague Eric Lin on that. Okay, and of course you can do the surveys and you can do the measurement. And actually, I mentioned about one of my PhD students is doing research on this area, just looking at the measurement and then adjustment. Measurement and adjustment to get the operational profile. Measurement of the past and looking at some forward adjustment and getting the operational profile. I think that is a very nice and innovative way. And as long now we just try to have some good case studies to show that this is a viable and effective procedure. And so we are working on that and try to get that published as well. Okay, and with the Markov operational profile, you can use some of the structure and the domain knowledge to help you with the construction of operational profile. Okay, so that is actually one of the kind of advantage of this over the mutual operational profile, because you have some local information you can use, and then local information is typically easier and more accurate than the global information, because you are looking at the under this specific situation, what are you going to do? Not asking a general question, what are you going to do? I don't know. I do all kinds of things. Okay, but under this particular situation, if you pinpoint down this one, either ask the customer or you do the measurement, you are more likely to get accurate and more precise answers. Okay, and you can, if you are doing the UMM, collection of Markov OPs, operational profiles, Markov chains, then you also need to make some adjustments and decision about where do you break up the hierarchies and things like that. Okay, so that's the general ideas about this. And then there are some other sources for this information sources. So whatever sources you use for financing machine, well, you can use it for Markov chain because that gives you the basic structure. Okay, and if you have some existing flowchart and the testing models and all those things, that can be the basis of your Markov chain as well. Sometimes people do have the performance models. Okay, they use Markov chains for lots of things, queuing theory, queuing networks, and a lot of those queuing networks looks remarkably similar to some of the system operations you want to model. Okay, so for example, in the operating systems, you look at some of the state transitions. That's kind of it's like the external view of the operation of your system. Okay, and you can directly use those kind of things. And then when you look at this, they have maybe waiting at the various different things for I/O, for disk, for memory, for CPU, for this, for that, and then you can connect those things, and you get your kind of a basic Markov, basic financing machine, and then you look at the routing probability when you have things, say for example, in the operating systems. After you finish with the CPU, there's some kind of CPU computation there. Maybe some of them will go waiting for some logical conditions, some of them waiting for the disk, some of them waiting for memory, some of them waiting for some external storage and the graphical processing or something like that. And then you can look at how likely you are going to wait for this, wait for that, and wait for that, and then you get your Markov operation profile. Okay, so you can reuse a lot of those performance models, system models, operating, all kinds of things. And then you can use some of the analytical models, queuing models as well. You can look at the market requirement analysis and so on. But essentially, it's a kind of a black box with more focus on not only on the user's usage, but also the quantification of their usage. Okay, and then you can use this one to get the for finite state machines and then transition probabilities. If you have some existing hierarchy, oftentimes it can be mapped into your UMM hierarchies. Okay, so for example, one of the things we did with the web testing for the SMU website is that we looked at the organizational structure, and we can identify some of the things. And actually, we did some cross-reference empirical comparison. We found out that within each of the organizational unit, usually you have a much more kind of cross-references than you have across the different department boundaries. Okay, so for example, there are lots of linkage between the one web page of the CS belongs to the CSE to web domain, then there's a CSE to say civil engineering. Okay, and so we can use that kind of organizational hierarchies to sometimes as the initial UMM hierarchies as well. Okay, but other times that maybe if there are tight links between some of the things, then you have to make some other adjustments. Okay, and once you have the model, you can do a number of things. You can do the analysis, you can generate test cases, and then when you have the result, you can do some further analysis and use some of the theoretical foundations. Okay, so once you have the chain, you can do immediately. You can do some of the kind of analytical kind of things about this. Okay, so for example, that you look at the chain, what kind of property, what kind of chain this is. We mentioned about recurrent Markov chains versus the transient Markov chains. Okay, or absorbing Markov chains. Okay, so with the recurrent Markov chain, so you will be repeating things forever. Okay, so will not be observed in some states. With the transient Markov chains, is that you will be observed into some observing state. Okay, and then we can look at some of the things. For example, that with the recurrent Markov chains, there's some theory about Markov chain about how do you solve the Markov chain to get the frequencies at different states. Okay, remember I mentioned about there are some of the things about how often you visit this. It turns out that if you have a stationary chain, then you will have a probability distribution of among your states. Okay, that will add up to 1. How do you do that? Is that you can solve a linear set of equations. Okay, and so in the book there, I went into a little bit more discussion about that, but I don't want to emphasize that too much. But that's something that you may be considering. Look at the stationary thing. But the thing is that with difficulty with that is sometimes you have the process may not be stationary. If it's not stationary, then what you can do is you can only approximate the state probability, okay? And then by looking at some measurement and simulation, okay? That's a little bit more theoretical than I want to get into, so I'm not going to get into the details, okay? Then with the test result, because you have the Markov chain, actually you can go further than individual test result, okay? For example, if you have a Markov chain like this one here, then you have a result to say, okay, how reliable this thing is. You look at the problems. You look at the testing and you look at some of the failure observations. You say, okay, I observed some failures in this final state. Well, it's probably not going to affect those other things, okay? So because of the Markov chain property here. But if you have something here, it's probably going to affect a lot of things, because this is an important decision node that branching off into these 3 things. And then imagine a large Markov chain. Some of the nodes may be more highly connected, have higher connectivity to the whole thing. Other nodes maybe it's almost isolated node. Okay, so you can look at the connectivity of the things and look at the probability of visiting that node, and then actually if you have some problem, some information about how likely that node is going to fail and things, you can actually generalize based on the Markov chain how the whole system will perform. Okay, so that is actually a very interesting research area. And one of my former PhD students actually initially want to get into this, but this kind of turned out to be a fairly difficult theoretical problem. So he made a little bit of progress, but didn't go too far. And then he found some other interesting things, and he finished the PhD without finishing this part. Okay, that's okay. That's you find whatever that's interesting, and you solve that problem. Not necessarily you always have to solve the problem you started up with. He started with this and then found out it's really kind of difficult to do some of the things, and he was doing some simulation and doing some theoretical analysis, and got into kind of some trouble, and he took several courses from the statistics department, and eventually didn't go too far in that area. Okay, and so the test case generation. This is interesting because here with Markov chains, we are not just talking about the complete operation, because with MuSA we have the operation that we kind of assume that you have the operation and that's it. You can just play that operation out, and that's your test case. But with Markov chain, that the thing is that you do have the states and the transitions. When you do the test, you will go through a number of states, a number of transitions. So you need to kind of link them together. And when you try to link them together, you have to determine which one you want to link together, because this is probabilistic. And how do you do it? So generally, there are 2 essential ways of doing it. One is the kind of pure probabilistic way, and another one is the kind of pre-generated test cases. Pure probabilistic way is that you would look at, well, if this is your Markov chain, then I use your Markov chain. I just start from here, and then decide what to do next. I can, in this case, I only have one decision to make. only one choice. So I have to do this way, have to go this way. Over here, I do have a decision to make because I can go this way, or go this way. Go to B, go to A, or go to D. Okay? Then how do I decide? I look at the probability. So I must have some kind of a probability distribution to consult and see. Then I have 0.89 probability of going this way, and 0.01 probability of going this way, and 0.1 probability of going this way. So essentially, I do a kind of a probability determination and I say, this time, what do I do? I flip a coin, or doing something, and then I have some kind of a random number generator or some kind of a determination, and then I say, okay, I'll go this way. Next time, probably I'll go this way again. Next time I go this way again. Next time, maybe I'll go this way. Next time I go this way again. And so you can do this dynamically. As long as you observe the user probability distribution to get you, and then eventually the number of times you follow this thing will eventually converge to this number. Okay, the number of times you follow this thing will eventually converge to this one. So it's out of 1%, 10%, and 89% of the time you're doing this and that. Okay, so that's one way of doing that. That's a kind of a more puristic way of doing that. Okay, you look at the pure probability that are doing this way. But this one poses some of the difficulties. Okay, because you have to, instead of just doing the testing here, you have to do the probability simulation and the probability decision making, probabilistic decision making, which may take some time to do. Okay, so it may interfere with your testing. So what you can do is that you can pre-generate and see how likely this one going to be the probability, and then do it. Okay, so that's the more of the kind of common way of doing this. Static, offline, you generate the things, determine how likely this is going to be, and then decide whether to run it or not. Okay, so I generate this chain out, and I say, oh, this had a high probability, I will run it. I generate this chain out, I say, this is not very likely. I'm not going to run it next time. But after I run this one a few times, maybe I will start to run this. Okay. So that's the basic test case generation part. Okay. And in the book, we talked about some basic work of Whitaker and Thompson's paper, and they basically try to use that dynamic approach, which may be pure, had the purity, but had a little bit less of the practicality involved in there. So the more realistically, people use some of the pre-generation. So one of the things that was a kind of important paper published in that area is a paper by Elaine Wayuka and her student Avricer. Okay, they did a paper. They essentially say, giving a Markov chain. Now, what I do is that I do 3 kind of coverage. Okay, and this coverage is actually based on the probability. Okay, so they do 3 offline test case generation, and then they decide to use something, and then to do the things that they have 3 coverage. One is the probable path coverage. One is the node coverage, the node coverage. Okay, and one is the call pair coverage. Okay, so essentially what you do here is to generate out of those things and rank them, and then decide, giving a threshold, what are the things that you need to test, what are the things you don't need to test. The things you need to test, you probably test proportionally or with the basic coverage. That's up to you. But if you are doing the usage-based testing, you test proportionally. Okay. So let's go back to this example that we can take a look here. Desk camera. So the 3 ways of doing this is the first one is the path coverage. Okay. Actually, let me do the easy one first. Call pair coverage. Call pair coverage is basically looking at the transition coverage or link coverage, which is actually not very meaningful here. In here, for example, we have this one. This probability is 1, right? Only one choice. This probability is 1. this probability is 0.01, 0.89, 0.1. Okay, so what you have here is that when you look at this, you have AB that's this is a 1, so AB is a 1. Okay, and the BC at 1, BC. Okay, and then you have the next one is a CA. CA is a 0.89 here, and then you have the CD. CD is this one, and then the last one is the CB. CB is kind of like almost 0, is 1%. So then you decide what kind of coverage criteria. You say, I cover everything at 0.1 and above, so you will select 1, 2, 3, 4. If you say, I cover everything at 0.01, you cover all 5 here. And you say, I cover everything above 0.5, you cover this 3. Things like that. So that's the call pair coverage. Call pair coverage is not so meaningful because that you may have a high probability with a call pair, but that still have a low usage because you very rarely visit that particular state, right? So from that state, you maybe have a high probability of following this one, but that state probability may be low. So to solve this problem, they say, okay, you need to look at the state probability. Okay, when you look at state probability, you have to solve the things about how likely you are going to be in this state, how likely you are going to be in this state, how likely you are going to be in this state, how likely you are going to be in this state. Then one way of solving this is solving through the theoretical framework about how often you are going to be in one of each state. Okay, and you can solve that. But oftentimes you may have run into difficulty with the theoretical solution. In that case, what you can do is to do some measurement and simulation and measurement, okay, or take some actual measurement or do some simulation and measurement, and then say, okay, I run it. I take 1,000 snapshots. Out of this 1,000 snapshots, because each snapshot you will be in one of the states, okay. I found out, okay, so for example, maybe I have 250 times I'm here, okay, and then maybe I have 230 times I'm here, and some numbers and the thing, and 500 times I'm here, and then only 220 times I'm there, and I can find out, and then I can say, okay, now it's only 20 times, so 20 out of 1,000 is 0.02, okay, and so this one, although it has a high transition probability, it's actually taking this transition is not so often. Okay, so you can do those kind of things, and then you can do the testing. So you can do the node coverage or the state coverage, okay, or they will look at the proportional state coverage. But this all those things is kind of still looks like more like a music operation profile, not really Markov, because you look at one thing at a time, right? So really, to look at the multiple things, you have to kind of connect them together. So that's their first thing is the path probability. So when you look at path probability, I can look at, okay, what are my path probability? I start with A, always start with A. This is my initial one. So what's my path probability? AB is one path. What's the probability of having this? Okay, that's 1, right? So when I start with AB, okay, and ABC is still 1, okay. ABCA, that's 0.89. Essentially, how do I get 0.89? So this times this times this, right? This probability, this probability, this probability, the product of all those things, okay? I can be A, B, C, A, B, C, A. Going to twice, then it's that 0.89 squared, right? And then I can do this, and I can do this, and I have, for example, I have A, B, C, D. That's what? 1, 1.1, so it's a 0.1, which is going to be lower than this one and lower than other things. So I can enumerate this out, okay? When I enumerate this out, I can say give me all the paths, execution paths, above certain threshold, I will test it. So you can do this. This is actually more kind of reflexive of the basic idea of usage-based testing with the Markov chains. Okay, and this is actually precisely when you have a Markov chain, how do you convert it into a Musa operational profile? Okay, so essentially what you have here, look here, this is your Musa operations, right? And those you have the probability, then you can renormalize them, okay? And then you get the Musa operational profile based on this, this thing, okay? So what you have there is that if you have a Markov chain, you can enumerate out the operations and calculate their probability. But the thing is that you say, oh, this one, I have this loop. It can go on forever. Well, it will not. Because if you're giving a threshold, you say, I'm not going to test anything below probability of 0.01. This one, every time you go through the loop, because there will be something to go out of the loop, outside of this thing, you will have something multiplied that's less than 1. When you have something multiplied by less than 1 enough times, you will go down to 0, go down to close to 0, right? So for any threshold, the number of paths will be finite. And then you can generate those paths, rank them. That is going to be a Musa operational profile. Okay, so you can see here, from the, if you have the Markov chain, you can actually generate some kind of operational profile similar to the Musa operational profile, test the complete sequences, that the sequence will be chained together by your Markov states and transitions. Okay, so that is a part of your homework assignment, so you can read more and then some of the things. So when you do it, it will become more clear, and so that's why I want you to do a little bit of that. Okay, and so that's the testing test case generation from Averiter and Wyuker. Okay, and with the UMM, we have some additional things. Is that we also look at the level and the level coverage and the things. So I'm not going into too much details there. And we have some things about the web testing. Okay, so essentially that's a continuation of our previous case study. We said that with web testing, when you have just use finite state machines, so then you have a state explosion problem, too many states. Okay, so what we can do is try to look at how do you reduce the states while still testing adequately the web applications. But then we found out that in terms of data sources, so if you want to do usage-based testing, we said that you can do actual measurement, you can do expert opinion, you can do survey. With the web pages, actually actual measurement will be a little bit easier than with most other things, because with the web applications, you do have web logs. Okay, you have the typically in this case is that we will look at the server logs. We can analyze the server logs. Those are the actual measurement of your customer usage, and process the server logs that we can get the usage information and build our model. Okay, so that's the basic idea there, and so we have the models that are UMMs, and we have the Musa operational profiles. So we use the data from the web logs. Okay, so I can briefly highlight a few things, and we analyze the web logs and connect them, and then we get our information. Okay, so for example, that we can look at the entry page to our website. We found out that our index.html is the highest used entry page. Okay, so that 18,000 or so entry pages are here. So that the previous page is not a SMU domain, And now the first page in the HTML domain is the index.html. Okay, and then we found out it's interesting that the entry pages is the index page for the whole school, entry page for civil engineering, I think. That's computer operations, civil engineering, SMU, something. And oh, that's a computer operations. They have some cameras, and so some people, I don't know, somehow they bookmark that have cameras, so they always want to look at it. At that time, we had some construction going on or something, so people want to look at the construction cameras or something. Okay, and we have CSE. Actually, CSE people are not that heavy users with the CSE index page. Maybe we are more specialized. We go to our own personalized things. Okay, so we don't rely on the overall index as much. Okay, and so we can connect the things together. Okay, so in this case is that we look at the referral information from one page to another, and then we connect those things, and then we build this kind of Markov model. Okay, so that's the case study. And I mentioned about the conversion between the UMM and Markov operational profile and MUSA. Okay, so from the Markov operational profile, you can convert it to MUSA as long as you are giving some kind of threshold, cutoff threshold, because you want to eliminate those infinite long sequences. Okay, but from MUSA, if you want to build a Markov, it's probably going to be hard. Okay, so but the MUSA things are simple, it's flat, it gives the whole operations. Markov break down the operations into individual stages, and then give you some localized information about the probabilities. Okay, so for the Markov operational profile is probably more powerful. MUSA is simpler, so it's they have their own advantage and disadvantage. Okay, and there are some kind of common things about how do you get the information, how do you construct the operational profile, and there. So in terms of the choice, is that really look at your application. If a kind of state transition is natural to you, then use some Markov or OP. If it's a kind of a one lump sum kind of operation, MUSA OP is simpler, and if it's adequate. If something simple is adequate, use it. If it's not, then try to use something else to capture the information. Okay, and I talked a little bit about the conversion here, and MUSA to Markov generally you don't have enough information because you don't have those state transition things. So you need to collect more information. Markov to MUSA is actually simple, a little bit easier, but you have to give some kind of threshold and stop. So that's kind of finished up this one, and you do have a homework assignment, and so that will help you kind of have some more hands-on experience with this kind of modeling and modeling technique. Okay, so that's it for today. Good night, and I'll see you next week. Okay. We don't have the end of class thing, so I'll put up this one. End. The end. Homework? Send me an email. Yeah. Remind me. Yeah. You'll have another exam too? Okay, sure. Also send me an email, and so I'll forward it to the grader. Yeah. No, because I gave the approval, so I will forward it. I collected those things, and I said I'll tell the grader I gave those people. You can keep it. Yeah, we are supposed to keep some copies for ABET, and so I made some copies.
Just